In this video, we would like to present our work to be appear on transactions on machine learning research, adaptive multi-step refinement network for robust point cloud registration. Point cloud registration, or PCR, estimates the optimal rigid transformation between two point clouds. Recent researches in point cloud registration focus on learning-based methods, particularly feature matching techniques. While they have shown impressive performance, learning-based point cloud registration encountered challenges in low overlapping scenarios, where the overlapping rate is lower than 30%. The seminal work GeoTransformer erroneously matches one point in the source point cloud to points outside the overlapping region. The recent work Peel introduces a post-processing method to refine the registration results. It utilizes the overlap estimation of a pre-trained PCR network, for example, GeoTransformer, as auxiliary information, also referred to as prior, and incorporates this information in the refinement network to improve the estimate. By employing the same network repeatedly, Peel establishes a multi-step approach and demonstrates enhanced performance. However, despite being utilized in multiple steps, the refinement network is only trained for a fixed mapping from prior to ground truth, not considering the fact that the priors become increasingly accurate throughout the refinement steps. In this work, we propose a simple yet effective method that enhances multi-step registration by making the refinement process adaptive. Our proposed framework for point cloud registration has three main parts. First, prior creation generates a series of rigid transformations with different levels of accuracy using a degradation function. Second, adaptive training uses these transformations to train the registration model across various step indices. Finally, during inference, the adaptive refinement network produces the final estimation. The model consists of 5 key modules. First, we extract superpoints from two overlapping point clouds, P and Q, using kp-conv. Second, we derive matchable superpoint features with transformers, using multi-head attention. Instead of standard self and cross attention, we introduce a generalized one-way attention mechanism that integrates overlapping information from the previous step. Third, we compute a patchwise correspondence map. Fourth, we refine these correspondences to obtain fine-level matches. Finally, we use a robust estimator to produce the final registration result. The main technical contributions of our method are the data creation and generalized one-way attention. Previous work, Peel trains the network F to map prior to ground truth. This, however, has a limitation: the model does not adjust to the improved quality of the prior during the multi-step refinement process. To adapt the multi-step refinement network to each step, one should specify the refinement FK that each step should perform. We propose to sample priors for each accuracy level by interpolating between the GeoTransformer prior and the ground truth. Given the nonlinearity of the transformation space, we define the degradation within the spherical linear space. Thus, we can create diverse datasets for the model in different step. Besides, we incorporate overlapping information through a one-way attention mechanism, akin to the masking technique prevalent in transformer models. To be specific, the input of the one-way attention is the feature of the points in the middle of the network, and one-way attention attempts to establish interactions between point features to update it. We define the points in overlapping region as anchor points, then we use the anchor points as the value tensor to rebuild the feature of non-anchor points. Here are the registration results on 3D match dataset. We compare our method with recent deep learning-based baselines, including 4 local descriptors, such as FCGF, D3 feed, and 10 transformer-based methods, such as GeoTransformer. In PCR, RR is the most critical metric, which directly measures the registration success rate, RMSE smaller than a threshold. Our method achieves the highest RR across different numbers of correspondences. As for 3D low match dataset, compared with the multi-step method Peel, our method still achieves notably better results. We attribute this improvement to our adaptive refinement design and our one-way cross-attention mechanism. Notably, our method with 5 iterations achieves an RR of 80.4%, which surpasses Peel's performance with 10 iterations. Our method also outperforms DiffPCR, which is a diffusion-based PCR network conditioned on the matching matrix. Here showcases qualitative results of our method applied to point cloud pairs with exceedingly low overlapping regions. For comparison, we also show the alignment results of our baseline geotransformer, cofinet, peel, and the ground truth. Our method accurately aligns the point clouds in these challenging settings, while geotransformer and peel get completely wrong results. To summarize up, in this work, we propose an adaptive multi-step framework for point cloud registration. To make it possible, we introduce a data creation method by degrading functions and a generalized one-way attention. In the end, we achieve superior registration recall rate on both 3D match and 3D low match. Thank you for your attention.